All right, last video for Chem 30. Once you have watched this, you will have pretty much learned everything that you should have learned for this course. Obviously, there are videos missing for the content that we did in class, but for everything that we have done online, this is it. This is the last one. So in this one, we're going to basically talk about all the theory stuff. So we're going to look at collision theory. So you'll see when you take first year university, you spend a lot more time talking about collision theory, rates of reactions, reaction mechanisms, but we don't really get into that. We kind of just gloss the surface of all of this, okay? So we talk about rates of reactions. So rates, we've talked about this before when we were in equilibrium, refers to basically how quickly the reactants turn into products. Okay, generally you will find that over time the rate of a reaction is going to slow, and that's going to happen because over time you're using up more and more of those reactants, and there's less of them available to be able to actually react. This isn't always true. There are some reactions where that doesn't happen, but for the most part that's what we are going to find. So for a reaction to be successful, and when we say successful we mean for those reactants to come together and turn into products, there's two things that need to happen. The first thing is they have to collide with the correct orientation of reactants, right? If you think back to Chem 20 when we did bonding, remember all of those shapes? There were very specific spots for things to go. They couldn't just go wherever they wanted. So what we find is if those molecules don't collide correctly, they're never going to turn into products because they're not in the right orientation. And the other thing we find is they have to have sufficient activation energy, which we abbreviate to a capital E with a subscript of A. Okay, activation energy is basically the amount of energy that we need to put in to break those initial bonds, right? Remember we've always said there's two steps to every reaction: breaking bonds and forming bonds, and that breaking bonds always requires energy. So we have to have that minimum amount of energy to be able to break those bonds. Otherwise, we're never going to form products because we can't actually break those bonds. So looking a little closer at that orientation, if you look here, here's basically some samples of some collisions. So the reaction is NO plus NO3. And what we're trying to do is transfer one of those O's from the NO3 over to the N of the NO so that we can make two NO2s. Okay, so when you look here, you can see that a bunch of these aren't going to work. Right here, the O is hitting the O. Well, that's not where it needs to go. It needs to go on the N. That's not going to work. Here, there's an O hitting an N, but it's the wrong N. We need it the other way, so that doesn't work. Here's the two N's that are hitting each other. That also doesn't work because that's not the transfer we're trying to do. So here, finally, we have an O hitting the N. The problem? It's not the right angle. So even though we have the right atoms coming together, they're not coming together with the right orientation, so it's still ineffective. Finally here, you can see it has more of that 120 degree, which is that angle we're looking for. Okay, we're never going to give you pictures and ask you what's going to be successful and what isn't. I'm just trying to illustrate to you why many collisions don't work. Many collisions don't turn into products because they just don't hit the right way. And if they don't hit the right way, they never stand a chance of actually forming products. So that's one limitation as to whether a reaction will occur quickly or slowly, is are they hitting with the right orientation on a frequent basis or an infrequent basis? Okay, the other factor is that activation energy. Okay, so activation energy is how much energy we need to put in to be able to break those bonds holding the reactants together. Okay, so activation energy is basically defined as the minimum collision energy required for a successful reaction. If you don't have enough, you can't turn into products because you can't actually break those bonds, right? Often I'll kind of compare that to like a high jump, right? Some of you can make it over the bar, some of you can't. Right? To be successful at the high jump, you have to actually make it over the bar. You have to have enough energy to be able to do that. Same thing happens with our chemical reactions. They need enough energy to overcome that barrier. If they can't overcome the barrier, they can never turn into products. So generally what you find is that reactions that have lower activation energies tend to happen faster because more molecules have that amount of energy. But reactions that happen slower tend to have much higher activation energies because most of the molecules are not hitting with enough energy. So far the only type of curve we've really looked at is a potential energy diagram, right? Remember in potential energy diagrams, we kind of had this, oh sorry, I'm in arrow mode. And then we kind of did a line here and a line here, and then we did that arrow down or potentially up if it was an endothermic reaction. This is a different type of graph. This isn't a potential energy diagram. This is a kinetic energy diagram. It's also known as a Maxwell-Boltzmann distribution curve. So the more area that's under the line, right? So right here is where I have the most area under the line. That's where most of my collisions are occurring. They're happening with that quantity of energy. I have fewer under here, and I have fewer under here. So here is your activation energy barrier, because this is energy on this axis. So what you find is that it's only these collisions over here that are going to be successful. So if you look at that, right, if we consider all the space under the line to be 100%, you'd probably estimate this as being, I don't know, 15, 10%. So what that means is out of all of these collisions, it's only 10 to 15% that's actually going to be successful. That's not going to have a very high rate for our reaction. Okay, but you're going to find that there are some ways that we can manipulate the rate of reaction, okay? Some of you are thinking, I can manipulate with a catalyst, right? And you definitely can. The other way that we can often manipulate a rate is by changing the temperature, right? Generally, you guys know that the hotter you make something, the faster a reaction is, and the colder you make something, the slower a reaction is. And the reason that happens is as we increase the temperature, remember temperature is a measure of kinetic energy. We give our molecules more energy. So if you look here, here's T1. So there's my original curve with how much are going to be successful, right? So it's only this that's being successful. But now you have T2, which is a higher temperature than T1. So we've increased the temperature. You'll notice that your curve shifts over to the right. And so what happens is, by giving them a higher temperature, I've given my molecules more energy. Because my molecules have more energy, more of them are now going to be able to overcome that barrier. Right now, it's all of these that have sufficient energy to be successful. So increasing the temperature is going to increase the rate of the reaction because I've given my molecules more energy, so it's easier for them to overcome that activation energy barrier, right? And what's not in this graph is, what if I made it colder, right? Because remember when we were back in equilibrium, we talked about like, oh, if we make it colder, it's going to favor the exothermic direction. And there were some questions about not actually making it too cold. So now hopefully you're going to start to understand why that is. Because let's say I made it colder. If making it hotter shifted my curve to the right, made it colder is going to shift my curve to the left, right? So I'm going to find, well, I wanted to make that a little higher. Hold on. I'm going to find that now my curve is going to look a little more like this. And so now it's only this little teeny tiny bit that's actually going to be successful, right? So we can say that this is T3, which is going to be less than that T1. Okay, so there's a lower success because our molecules have less energy. So this is why generally we don't actually want to make it super cold, even if Le Chatelier tells us that something would be favorable, because nothing actually happens, our reaction stops, okay? So this is one way in which we can speed up the rate of a reaction. We can give our molecules more energy, makes it easier for them to overcome that activation energy barrier, and we're going to see that the rate of that reaction is going to speed up. So now we start looking at still potential energy diagrams, right? So we looked at these before. The difference was, like I kind of sketched here, we just had this, right? And then we had our little arrow kind of going down, or potentially our line was up here and we had an arrow going up. Now you're going to notice there's this extra part in the middle, right? From here to here, this part here has basically been inserted in. This is your activation energy barrier, okay? So delta H is still the difference between the reactants and the products. That doesn't change. That's always what delta H is. But now you're going to notice we're going to talk about the activation energy of the forward and the activation energy of the reverse. Okay, so activation energy of forward and reverse are not the same, right? If you think about delta H, if we switch from forward to reverse, all we do is switch the sign. But if we're talking activation energy, it's very different. So if we're looking at the activation energy of the forward reaction, it's going to be from the reactants to the top of the hill. But if we're talking about the activation energy of the reverse reaction, now it's from the products to the top of the hill, right? These are not the same size. They are not the same. But look here, if I know the activation energy of the forward and I know what delta H is, I should be able to figure out what activation energy of the reverse is, because these two added together are the same as this one, right? Obviously, I wouldn't be using the signs, but yeah, we could figure out what it is. And the same thing is true over here, right? In this case, the activation energy of my forward is going to be much larger than the activation energy of my reverse, because this is much higher than this is. But here, I could figure out the activation energy of the reverse, because if I knew the activation energy of the forward and I subtracted delta H, I could figure out what that value is going to be, okay? So what this means is that you find that the forward and the reverse reactions have different activation energies, which is why they'll often happen at different rates, even if we start them at the same concentrations, because of the different minimum energy requirements that they have. Okay, so this slide kind of just describes to you exo-endo, right? We're still seeing exo and endo the same way we did before. We're looking at where's the reactant, where's the product. In this case, to get my delta H, I am going down. So that would mean delta H is negative. So this would be an exothermic process. Here, going from reactants to products, I'm going up. So this would have a positive delta H, and it would be an endothermic reaction. Okay, this one here describes to you how you would go about calculating those values from those curves, which I talked about while we were looking at them. So here we break down this reaction a little bit more. You can kind of see what is happening as we migrate up the hill and then down the hill. So here we start with our reactants. They're two totally separate molecules, right? So here's my bromomethane, here's my hydroxide ion. They are two separate things. As we start to move up this activation energy barrier, we find that our bonds are slowly going to start to break. So this carbon to bromine bond is going to start to weaken. And we're going to find that this hydroxide is going to start to form a really weak attraction towards that carbon. By the time we get to the top of the hill, so we get to this position here, we have what's known as an activated complex. Okay, you will also sometimes see, where do I want to write it? I guess I could try writing it here. Maybe it'll let me write here. It's also called a transition state. Okay, and we call it a transition state because have a look at what we have here. It's kind of a hybrid between what our reactants were and what our products were, right? This carbon is kind of still attracted to the bromine, but it's also kind of attracted to this hydroxide. So it's this activated complex or transition state that's halfway between reactants and products. It either could go back down and turn back into the reactants, or it could go this way and turn into the products. Okay, if it does have enough energy to get over the top of that barrier, you're then going to find that that bromine bond is going to get even weaker still to the point that it's barely existent. And this carbon to OH bond is going to start to get stronger. And then by the time we get to the bottom of the hill, we're going to release that bromine. This new bond will be entirely formed. So breaking bonds, we have to input energy to break them. We get to the top, we have an activated complex or a hybrid transition state. And then as we come back down, we get to release energy as we form those bonds, right? Remember at the start of the unit, I said whether a reaction was exothermic or endothermic depended on how much energy it took to break the bonds versus how much energy was released. So you can see here that the amount of energy being released as the new bonds are formed is greater than the amount of energy that went in to break those bonds. That's why when we look at delta H, it's going to be a negative delta H because it's going down. So this is overall going to be an exothermic process because we have broken those bonds and released more energy as we formed them than we did as we broke them. Okay, so things you should be able to get out of a graph like this. You need to be able to recognize where is that activated complex or transition state. You should be able to recognize where is the activation energy of the forward, where is the activation energy of the reverse, and how do I go about determining what is the delta H for my reaction based off of the information that I have. Okay, one thing you're going to find, we do not get into calculating EA of these reactions. The only calculations we're going to do is if they give you one and they give you delta H and they ask you for another. Okay, there's no data table for you to really look these up that you have access to in your data booklets. That's definitely getting into university territory to actually calculate those EAs because you have to do a series of multiple reactions and tests to be able to calculate that. Okay, so let's look at an example where we are going to basically generate this equation. Let me just change that capital D for delta so that it's actually the right symbol. Okay, so draw a potential energy diagram for the reaction of carbon monoxide and nitrogen dioxide to form carbon dioxide and nitrogen monoxide. So it's given us the activation energy of the forward and it has also given us delta RH. So we are going to start by putting in our X and Y axis. Okay, so on X, we are going to put reaction progress. And on Y, you're either going to put H or EP, whatever you want to put. Okay, and this is going to be measured in terms of kilojoules. Okay, so we need to put a line for our reactants. So I'm going to put a line. Okay, so we're going to start by following the same set of instructions that we followed before. Right, we put a line. Remember, underneath the line, we write the word reactants. Okay, above the line, we're going to write what they actually are. So we are using carbon monoxide. That's right. Plus nitrogen dioxide. All right, where are we going to draw that product line? Well, we're going to decide where to draw the product line based off this delta H. So delta H is negative 226. So I should be drawing it somewhere down here, right? So that this actually gives me a negative because I need to be able to recognize that this here is going to represent that delta H, and we know what delta H is, right? So we can write in here delta H is equal to negative 226 kilojoules, because we had that. Okay, here we wrote our products line, so underneath it, we are going to write the word products. Okay, above it, we will write what they actually are. So what do we have? Carbon dioxide and nitrogen monoxide. All right, so what are we still missing? We are missing our activation energy barrier. So how high should I draw it? Well, the activation energy of the forward is 134 kilojoules. So if this represents 226, I don't want to say this is half of that because it's a little more than half of it. But when I go to draw my curve in, I shouldn't make this huge curve because that wouldn't be accurate with respect to the numbers that I have, right? I should make it something that's smaller than that. So, sorry, I have to draw this. The pen. Well, that's actually not too bad. There we go. So, we have some other marks in here now. So now, from here to here, going from the reactants to the top of the hill, that is going to represent the E EA of that forward reaction, right? And EA of the forward we were given as positive, well, I meant to write equals positive 134 kilojoules. Okay, so other thing we need to add is what's the EA of the reverse? So the EA of the reverse is going to go from the product line to the top of the hill. I think that about lines up at the top of the hill. And then next to this, we are going to write EA of the reverse. So this one we have to figure out what it is. We know that this is 134. We know that this is 226. So we're going to do that 226 plus the 134. And we are going to get that is positive 360 kilojoules. Okay. So you should be able to determine what some of these values are. The only value they're ever going to really ask you to calculate in one of these graphs potentially would be this, right? You could calculate the delta H because you could go to your data booklet and use those standard heats of formation and theoretically calculate what this number is. Okay, so we talked about how temperature can increase a rate. We also mentioned that a catalyst can increase a rate. So catalysts work different than temperature. Okay, they both have the same outcome of speeding up the rate of the reaction, but what's different is how they do that. So increasing the temperature increases the rate because it gives our molecules more energy and makes it easier for them to overcome the activation energy barrier. Catalyst doesn't do that. What a catalyst does is it provides an alternate pathway, and that alternate pathway doesn't have as large of an energy barrier. So a catalyst basically lowers that activation energy barrier. So by lowering the barrier, it makes it easier for those reactants to have the minimum amount of energy, because now we've said that that's not the minimum anymore. There's a new minimum, which is lower, okay? So same final outcome as temperature, but a different way of doing it. So on my potential energy diagram, which is what this is, I will see the effect of a catalyst because it is going to lower that energy barrier. On a potential energy diagram, I don't see any impact to that by a temperature change because temperature doesn't impact potential energy. It impacts kinetic energy. And that's why we looked at those Maxwell-Boltzmann distribution curves to look at that kinetic energy, right? So if we go back to the one that we looked at here, right, this was what we had, and we saw that by changing the temperature, we shifted the location of the curve, which is how we changed how many reactions were successful. But with a catalyst, I'm going to use this one because it doesn't have as much writing, we said that a catalyst lowers the activation energy barrier. So what you find is if this was my original activation energy barrier, it's going to lower it. So maybe the catalyzed one is going to come in over here. So this would be the EA of the catalyzed reaction. And so now what we find is because we've lowered that activation energy barrier, it's not just this that's going to be successful. It's now going to be all of this that's going to be successful. Okay, so two different ways to speed up the rate of a reaction. Changing the temperature, which is going to change how much energy our molecules have and make it easier for them to overcome the barrier, but the barrier itself isn't changing. Or we use a catalyst, which provides an alternate pathway, which has a lower barrier, which makes it easier for molecules to overcome because more of them will have that minimum threshold of energy. Okay, these next couple of slides basically just give you some examples of catalysts in the industry. So it talks about enzymes, right? Those of you that are taking biology are familiar with enzymes as being biological catalysts. You often learn about like the lock and key model for the substrate and the enzyme, and basically that lowers your activation energy because it ensures that they're coming together with that right orientation. Okay, there's also hydrogen peroxide that we talk about. Again, I want to say this is a lab you did in Bio 20. If you took Bio 20, you take hydrogen peroxide and you combine it with like catalase. This is basically why you see if you pour hydrogen peroxide on a cut, it's going to bubble. it just really speeds up that rate of decomposition of hydrogen peroxide, right? Otherwise, in your house, that hydrogen peroxide can last for probably a couple of years as long as it's stored in that dark bottle and isn't open frequently. Okay, there are some diploma questions for you how to look at here, right? So it's talking about activation energy, how much energy is released, talking about net energy, which is referring to delta H, talking about alternate energy pathways. Here are some more questions. So this is kind of more all that theoretical stuff for you to have a look at. So you can work through these questions. If you have questions about them, send me an email. We can set up a virtual classroom. But that is it. You are now officially done Chem 30, and hopefully you know all the different components and all the different units, and hopefully learning some of this on your own at home wasn't too bad. All right, thank you. Bye.